I want to start again with a short review, and this time rather than leafing back and forth, I'll just rewrote the things, the important things, so the last things I said. And I'll be doing now two-phase flow in porous media for a little while, and then I'll switch to the fiber bundle model. The reason for this is I sort of vacillated between, flow in porous media and the fiber bundle model. Both things are things I love, and January was fiber bundle model month for me. So I can't resist it. Just okay. But back to two-phase flow in porous media and the thermodynamics of two-phase flow in porous media. And I'm just showing one single aspect of it. Namely, I'm using this scaling law here. And remember what this was about. Okay, so you have a porous medium here, and the flow is like this. I make a cut, and then I look at the pore space I see in the cut. Part of that pore space will be filled with wetting liquid, and that has such an area. And part of the total pore area will be the non-wetting liquid, namely this one here. And what I'm saying is that if you change the size of your porous medium, okay, without changing the length of it, by factor lambda, well, that has the same effect as simply increasing the volume flow by this lambda. And then you start the machinery. That's back to Euler homogeneity. And what you find out is that you can then identify two velocities, and these we call thermodynamic velocities, and then they are simply the derivatives of the total flow rate, not the flow rate of just one of the fluids, but both of them. This AW and this AN. And then at the same time, you have the average wetting seeping velocity, which is the seeping, the wetting volumetric flow rate divided by that area, and the same here. They are not the same, but they are bound together through a function here. That's this form, and that defines a velocity scale, a velocity function. And that velocity function we call the co-moving velocity. And after some algebra, etc., one can show from this single assumption that you can express the wetting seeping velocity and the non-wetting seeping velocity in this way. This is the total average seepage velocity. This is its derivative. Here's the co-moving velocity, and the other one. So this is actually a velocity transformation. And now, here is the total flow rate. And that's what we found experimentally, this square in pressure. So this is a constitutive equation. This co-moving velocity is telling us something about the geometry of the porous medium, and it has this form here. So what you have here is a theory which is as complete as relative permeability, plus it is right. Because the only thing I've said here is this.
So how would the information about the exoder media come? So where does that come?
Where the...
So you had shown the flow through a, let's say, periodic some kind of structure.
Yeah.
So if you now have a disordered structure, what?
Disordered structure will show up in these coefficients, and it will show up in this thing here. These are the constitutive equations. Hmm? That is the saturation, that's the non-wetting saturation, that's the percentage of the non-wetting liquid of the whole pore volume. And this is the wetting one. And two-phase flow, and it is incompressible. It's also an underlying assumption here. But this is a complete theory, actually, and it only contains kinematics. It doesn't really explain, discuss forces. So that is the next step. And that's what I'm not talking about. That would be Gibbs relations and so forth. And that is to really understand this one here. But that's kinematics, and I think we have that under control now.
Provide a simpler
Yes. I mean, it's co-moving because, okay. These things, these velocities here will be correct if the bubbles did not get in each other's way. It is assuming a completely homogeneous porous medium without, and the liquids passing through each other without seeing each other. You have to compensate for that. So you write down the most general expression you can, and this is actually the most general you can ever think of. And then you have the transformation between the two. And then we simply go in and measure it in our numerical model, and we see that it has this form, and we have some analytical examples where you can go in, and it has basically this form here. And this is, of course, where the physics sits. I mean, this is the porous medium. It sits here, and it sits here in these coefficients, basically. And this is just thermodynamics. So it's the same thing with standard thermodynamics. You have all these amazing relations between quantities, but it is anchored in the equation of state. That is all the stuff you cannot get through the symmetries of thermodynamics. That's what we're trying to use here. And what I'm showing is that you can really go far with this. So I feel that way. But I have to say, to sell this to the porous media community is not easy. They are conservative. Huh?
What's wrong with that?
No, I mean... Oh, you'll get, I'll bet there's going to be 15 pages of referee reports on this. Yes. I mean, just the derivative, I mean, how to define the derivative. So we have to go through, really show it step by step. But anyway, what I want to go now is back to statistical mechanics. And because I started out, I mean, the first hour, I gave you a little, I gave you the probability, configuration of probability to find a certain pattern, and we use that to construct a Monte Carlo, for example, method. Okay, so I'm now going to try to make a connection between that and what we're doing here. Here's the porous medium again, seeing this from the side. Here's a cut. I'm now opening up, so I see here's the cut, and here's a blow up, and this is what I see, right? I have the wetting liquid and the non-wetting liquid. And if I count the brown ones here, I'll get a certain area. If I count the black ones, I'll get a different area. And the sum of the two is this one here.
So so you're showing one pole, or?
Now I'm making a blow up here, and these are the pores I'm looking down at. So this circle is just this circle here. Yeah.
And the assumption is that one pore has only one fluid.
No. It doesn't have. I mean that. It could be inside here. That will show up in this constitutive equation, films, etc. So that is not a requirement. Okay, so then, and I had this. That's the only assumption I did use before. But what I can do now is to go a little bit further. So here's my porous medium, and here is the total wetting area. That's all the black ones, and the non-wetting, all the brown ones. But I can now have a differential pore area. Namely, that is the wetting, the area per, if I specify a velocity, I'll have that this differential here contains that velocity. So it's basically a histogram of the velocities inside here. And that will depend on these two here. And I'll have the same thing for this one. And look, if I sum over this one here, I get the total area. So this is basically the wetting area of wetting liquid having a velocity v between v and v plus dv, and so forth. Here's the other one. All right, so I have now these two, and if I now want to calculate the average of any quantity, any function f of the velocity, well, I just have this one here and this one. And if I want it over both liquids, this was only over the wetting, and this is only a non-wetting, I just sum the two, and I end up with an expression like this. The saturation, the wetting saturation times the average over the wetting part, plus the saturation of the non-wetting times the average over the non-wetting part. And here I set up a generating function by just Laplace transforming the thing. And I'll have a total, then z, it's not perhaps so strange I call it a z, and I'll have, then there's a sum of the two here. And I'm introduced a parameter beta here. It only makes sense to set beta equals 0 here, but you know, this one with beta equals 0 is the area here, and so forth. And then, and I'll be very, very quick here, because I can, for example, then easily show that fluctuations over the velocity itself then have this rather complicated structure that falls straight out of it. And the total velocity, for example, is given by this. And what I'm not going to go further than this, but this is now the contact between the statistical mechanics and the thermodynamics I just showed. So this is how we think. All right. Now, this is the last thing I'll say about flowing porous media. And that is something we thought was a simple problem, but it's not a simple problem at all. And that is if you have miscible liquids, but still not so miscible that they simply get totally tangled up, what is the effective viscosity of that liquid? So we can try to use relative permeability theory here. That is this old 1936 theory that everybody is using and everybody knows is not right. Just see what it gives here. So we have here, here's the velocity, the wetting or non-wetting velocity. Here's the wetting or non-wetting viscosity, the relative permeabilities, and the pressures. And the pressures are then connected through this capillary pressure function. Now, I set this to 0 because we are turning off we are making the fluids miscible. And then I just add the two partial Darcy equations, and I get minus k permeability, pressure difference, and then just the sum here. And of course, this is 0, so the two pressures are the same. So that defines an effective viscosity for me. And what I find then is that the effective viscosity is then a relative permeability of the wetting fluid over its viscosity plus this one. Now imagine making the two viscosities equal. Then you get 1 over mu, but the sum here doesn't add up to 1, which it has to. So relative permeability simply fails completely in that limit. It is not right. It is not right. And there are hundreds of ways you can show that relative permeability is wrong. It's just one of them. All right. So what kind of effective viscosity would you give to this mixture? Would you do a harmonic average? Would you do a series arithmetic average, the standard average? Would you do a geometrical average? If you go in engineering literature, you'll find them all. You can then try with something general. have an alpha. If alpha equals 1, you have the arithmetic. If you have alpha equals -1, you have the harmonic, and 0, you get the geometric average. And actually, that has a name, this equation here. I didn't know it had a name, but it has a name. Well, the thing is that nobody has suggested this before. And this is our measurements, numerical measurements. They have to do this in lab. We're going to do this in lab. And then we got a real surprise. Because, all right, here are two-dimensional networks. Here are three-dimensional networks. You know, using our, you know, sophisticated network model. If you have bubbles, you do not allow many interfaces inside your pores. That means your pores are pretty big. I mean, compared to the bubbles, you get actually an exponent alpha equals 0.6. You see, you get here's SW. Let me take up the expression again. Here's the expression. Essentially, I'm using that expression. When I get the right exponent up here, I get straight lines when I measure for different viscosity ratios. So you get beautiful straight lines with alpha equals 0.6 in 2 dimensions and alpha equals 0.5 in 3 dimensions. But if you let your system have many bubbles in each link, then the exponent is 1. So there are two behaviors here we're seeing. We're seeing for small bubbles, alpha equals 1. If the bubbles tend to be large, you get a 0.6 in 2 and 0.5 in 3 dimensions for this exponent. So we're going to follow this up experimentally. We only have this numerically at the moment. So we'll see what we get. I don't know. Yeah. All right. And then I thought I'd just show you a fun experiment that has not been analyzed, but just show you what kind of experiments people are doing in Oslo. And this is just a Helle-Shaw cell, which is now standing. So 2 glass plates and standing like this. And it's filled with glass beads, but you basically cannot see them because of the viscosity match. And then they have put a pH indicator of acidity inside here. So that's something that changes color if it gets if the liquid turns acidic. And then the only thing they've done is now, at this very moment when I start this film, is to pump CO2. So there's a layer of CO2 sitting right here. That's all. You know, everything is tight here. Just a CO2 layer. And what you see is, well, that was not what you wanted to see. Oh yeah, here. The point is that the CO2 is reacting with water and making carbonic acid, which is actually has a higher density than water. So you get these things. It simply pulls the CO2 into the water. And then it's amazing that it's these big fingers, because there are these small things here. So, you know, there are just so many things to look at here. Yeah. Okay, so that was, I took it because of the color. All right, so now part 2, a fiber bundle model.
Just one last.
Yeah.
In this modeling, you have just simple liquid. I mean, in a sense, these are not Bingham liquids or anything. So, do you have any idea of who put Bingham liquid?
Bingham. Yes, I mean, there is some work on Bingham liquids in porous media, and that is very, very interesting. It gives, in fact, this square behavior. Let me see this one here. This one here. Everybody have been believing in the physics community that that's what you would get from if you have a Bingham liquid in here. But it's more complicated than that. And what we have looked at, and especially Laurent Talon Fast in Orsay, they have looked at channels. And it is absolutely amazing. If you have a channel like this, you have the flow, but then you have these islands which are sort of stuck inside there, which are solid. But still they sort of melt on one side and freeze on the other side, so you have transport through the solid. So it's a wonderful problem. But it is a lot more complicated. I think that's, you know, than this one. Yes. But not along these kind of ideas. Those are, we are at the moment alone in that. All right, so fiber bundle model. So I'll give you a short introduction. That was sort of what you asked for, just to repeat a little bit. Then damage mechanics. I try to put your formalism into the language of the fiber bundle model, and then I'll show you some new ideas in how to use the renormalization group to see what we can get out of that for these kind of models. All right. Well, I think one should see the fiber bundle model as sort of an easing model for fracture. And, you know, I started with studying these fracture problems in 1980s, mid-80s. That was the first time I saw a paper in Fusrev on this. And I got really fascinated, and it's been following me. And we have had all these models through the years. They started complicated, but become simpler with the years. But now, around year 2000, atomistic modeling took off completely. And you can really model materials now from the atomic level and up to the level of specks of material that we actually can see. And you know everything. I mean, this is, you have the experiments, but this, of course, gives you a lot more. But it sort of gives you what you think the material is doing. It's not what the material is actually doing. But then I was sort of in a state of deep depression because all this work is just lost, because what on earth do we need these simple models for when we have tools like this? But of course it is now more important than ever, because what you do with these libraries of data, I mean, you have to bind them, you have to try to understand what they're actually telling you. It's not enough just to look at pretty pictures, right? So it's more than ever are these models important. That's my philosophy. Right. And you know, I mean, easing model, I really mean that. It is a very simple model. It really contains, I think, the essence of what one sees in fracture phenomena. And so one can get a hold of the mechanisms through this. But it, of course, will never be accurate. I mean, you won't use that to construct an airplane, but you need it to understand the underlying physics. And we are physicists. All right, the simplest fiber bundle model is an equal load sharing model. And here it is. Two stiff clamps. And in between these stiff clamps, I put fibers. And these fibers are elastic up to a threshold, and then they break irreversibly. They all have the same elastic constant, and that's it. You apply a force, and you pull harder and harder, and you see what happens. It was first proposed as a model for non-woven materials in 1926 by Frederick Pierce, and was followed up by Henry Daniels in 1945 in a long, beautiful review article. And he basically demonstrated how deep the statistics is behind this model. And we got this photograph from Daniel's secretary, and she took a long time finding a photograph that would really show his personality. He was a fun guy. He actually wrote those in the 90s. He was still working. All right, so that is the fiber bundle model. Now, here is, you see it from the side. So this clamp is just sitting there. Here is the position of the lower clamp when the force is 0. And then you increase the 0, and you increase it by a factor x, some of the elongation here. And then the thresholds here have been drawn by from some threshold distribution, P of x, and x of k is now the threshold of fiber k. And here is the force you have to apply in order to break fiber number k. So these are the ones, k are the ones that are already broken, and here's the threshold, like this. So that's the essence of the model. And if you now plot f as a function of x, you see these are all straight lines going through the origin. So this is, you know, the linear elasticity until a fiber breaks. And then you drop, and then you follow another one of these things. So that's through the entire process. This is what you would see if you were controlling x. If you're controlling the force, as soon as you got to this point here, these fibers will also break, and until it stabilizes. You go up, and then you have another one of these, and these are the origins of these avalanches. And here is where you get the catastrophe. And these avalanches are then produced by this force being the product of a decreasing function with k, that's the number of surviving fibers, and a noisy increasing function. And sometimes this wins and sometimes this wins. And that produces this here. All right, sample fluctuations. So here's a single sample with 50 fibers in it. Here's a single sample with 50 fibers in it. And here's a single sample with 5,000 fibers. And in fact, the force is then simply 1 minus x times x if this is just a flat distribution of the unit interval. Then you get a parabola here. And here's the first time you'll see that there's something funny here. I mean, non-trivial. Really non-trivial, actually. The force fluctuations at a given extension x. So I stop here, and I make many of these samples, and I see just how they are distributed here. There will be a Gaussian. I measure the width of the Gaussian, and that's the fluctuations. And that gives me that the fluctuations goes like the number of fibers to minus 1/2. But if you instead look at the fluctuations of this point, this is the maximum of each. They don't scale like this. They scale like n to the minus 2/3. We saw this numerically, and we thought there was something wrong with this is the 90s actually. Thought something wrong with the random number generator, but it wasn't, and then we were not able to show it. And I worked with Per Christian Hemmer at that time, and he is definitely the Norway's best person on combinatorics. But Daniels had it actually in one of his papers, but it was very, very hidden. And then we found a very nice proof for it, but this is non-trivial. And there are many, many of these. Now, that was just the introduction. Now I'm coming to the real meat here. No, that is new stuff. It appears in this reference here, and you should notice it's submitted 18th February. So it was submitted this week. Right, okay. So first of all, okay, sorry, I'm shifting now notation a little bit because this is just taken straight from the paper. T is a threshold. And here is the threshold distribution in this fiber bundle. Contains n fibers. Huh? And I'm looking at now the cumulative threshold probability. This is a probability to find a threshold T or less, this capital P. And at a certain point in the process, I have n broken fibers. I divide that by the total number of fibers, and I call this D, the damage. And when n goes to infinity and capital N goes to infinity, I can still keep this a fixed number, and then this becomes a continuous variable. So damage mechanics, I mean, the concept of damage is right in that limit. Okay. All right. So now I'm going to do an energetic analysis of the fiber bundle. And I assume that there's a damage D in the system, and I have an elongation delta. I called it X earlier, sorry, but delta. So I pulled it out delta, and the elastic energy now in the fiber bundle is, well, it is n kappa over 2 times delta squared. That is kappa delta squared over 2. That is the elastic energy in one surviving fiber. And n times 1 minus d, that's the number of surviving fibers. So this is elastic energy sitting in the fiber bundle. The energy dissipated due to the failing fibers. Well, what I have to do is, what is the meaning of that? Well, I have now loaded my system up to a certain level, and I have D fibers who have failed. Each fiber fails when the elongation hits the maximum length it can have. So what I have to do is, so this is the elastic energy. Let me actually use this one here. So let's say this fiber has a threshold T1. So it broke when it was elongated to T1, and its energy when it broke was this, and that's what's lost. And then I have this T2, this is next one. And so I have to add up all the way until I come to the level where I've broken as many as I have, and they go in order. And, P of T, that is the probability to find the threshold of this level or lower. And if my damage is D, well, all the fibers with the threshold D or lower is dead. So that one I have to put to D, and I invert it. So then it's T equals P to the minus 1 D. And then I have to integrate, from 0 and D. So this is the energy lost in the fiber bundle. So I have then E. There's no delta dependence here. And you see, this is just a material property, because the only thing that's in there is now the thresholds. This one contains, well, the elastic response. All right, so I sum the two, and that is the work I've done on my fiber bundle in order to end up with a low D and a damage lower D. So this is it. This is the quantity. The damage driving force, well, I take the E part. Oh, there shouldn't be a minus there. I just got carried away. So it's n kappa over 2 times delta. And the resistance to the damage, that is YC, that's this thing here, and I get this. And the criterion we learned from Laurent is now this one here. So the total driving force here is then Y minus YC, which is this quantity here, and I just do this derivative. I mean, here I just take the derivative of this with respect to d, so I get a minus sign here, and this is gone, and then this becomes just p to the minus 1 d squared. So I have this one. The equilibrium condition is that the force, I mean, for driving force is 0. So I set this equal to 0, and we see that the solution here is this, or inverted, this. Okay? The force I mean, the physical force is this dW of d delta. And I get this. You know, it's just the 2 disappears and the delta rather than delta squared. And I put in on the equilibrium condition. And I end up with this expression here. And this is the usual average behavior of the fiber bundle. But I can do more. Let's see. Well, I can turn on, hit on. So, right. What I can do is I can now try to control the force rather than the elongation. So the first thing I do is I have, let's see which one, yeah. You see, if I now solve this with respect, I mean, with f, it is the usual expression I had. It's, and then I do a Legendre transform, u of f and d. So that is w of delta of f and d minus f times delta f. I plug this in, and I have this expression here. The damage driving force, I just now take the du dd with a constant force, and I end up with this expression here. The equilibrium condition, setting this equal to 0, solving for the force, gives me this. And that's the same expression as before, but it's sort of scrambled. Now it's a d here. Now before it was a delta appearing. And then if I just compare it with, I mean, combine it with this old, I get back my old expression. So it works out. Now, I'm not going to talk about local load sharing here, but it is a real challenge to try to generalize this to the local load sharing model. And I feel that if we can do it, we will really understand damage mechanics a lot better. Because then we will be able to see how the forces at the microscopic level is conspiring into making this a local variable on a microscopic level. We have not succeeded in this at all at the moment, but we're thinking along the following lines. Well, first, catastrophic failure. So I had this expression here. Now, this equilibrium condition can only be satisfied if we have this. And in terms of what this meaning of this is that if we're controlling the force, and the force has to be below the maximum of this here. If it's above, you're not in equilibrium and it will just break. So that sits there actually. But of course you don't have a condition like this when you're controlling delta. That's not there, but here it is. So you're basically getting everything. Now, the way I feel that we should try to approach the damage problem is to use the extremely powerful machinery of the Renormalization Group here. Because that will tell us how to coarse grain the system in such a way that we just don't destroy it. Which means we take our system and replace it by a coarse grain system that has the same properties on even larger scales. And in order to do that, well, first we have to understand completely the equal load sharing model, because that is simple enough for us to do things partially analytically. You'll see that we are going to end up with something quite non-trivial. All right, so this is how we approach the renormalization group. The background of the renormalization group is that that essentially solved the problem of equilibrium critical phenomena. In the 1970s, Ken Wilson did that. Personal anecdote, I was a graduate student at Cornell and I took the course on statistical, on critical phenomena from Ken Wilson the fall he got the Nobel Prize. And I'm looking at the notes. He really put his soul into this course. So that, my notes are absolutely beautiful up to the October 10th, and after that they're complete chaos. From that moment on, he was a public figure, and he did not deal with that very well. So he was in a complete state of total chaos. All right. But anyway, so here is the damage. But now we have to assume that n is not infinite, it's finite, and here is now the number of broken fibers. So let us use this notation here, and the meaning of it is just this. And also I put an n here on these quantities because they are finite, big but finite. And we see here that if I rescale n by 2, I divide n by 2, and I rescale n by 2, divide by 2, I get the same thing. So this is a symmetry. And now the idea is this. I have these n fibers like this. What I'm going to do is to replace these n fibers by a new fiber bundle, but with n over 2 fibers, half as many fibers. And I'm going to demand that, and this is something I want. And this is something you always have to do in a renormalization group. You have to something you have to keep constant, otherwise you go off somewhere. Don't know what you're doing. What I'm going to demand is that this energy function here with a fixed delta and this damage here, n and n, is equal to the same energy in a fiber bundle with half the number of fibers and half the damage. So what happens is that I have, for capital N, I will have n, capital N, different values that this n can take. What I'm demanding is that every second one of these, namely 0, 1, 0, 2, 4, 6, 8, and so forth, has the same value as this. Those in between I cannot say anything about because they're coarse-grained out. So I'm now coarse-graining this thing. So n goes to n prime, which is n over 2. Now, my fibers should have the same elastic properties, which means that I now combine 2 fibers into one, sort of. And that means that its elastic constant has to be going up by a factor 2. And I'm keeping the load constant. And that means that n times kappa remains a constant. So that will not change through this procedure. So that's a constant. Now, here is the damage. No, not the damage, but here is the dissipated energy. That has to have this symmetry. Okay? If I write it out in the continuum limit, that's what it looks like. But I'm saying this is a finite system, so I write it out in terms of sums. So what this one here is then just kappa over 2 times the sum of thresholds now ordered in sequence from weakest to strongest, summed up to the right level of damage, and that has to be equal to, well, 2 times kappa, or 2 times new thresholds here. Then this will remain the same. Remember, parenthesis here means that they are ordered. The RG transformation, and I have to transform now the thresholds. So what I have to do is I have to find a way to transform this into a set which is half as large, but in such a way that the dissipation is the same. And there are many ways of doing this. Because remember, all I want is that this is equal to this, and I can do that in umpteen different ways. So why not use a simpler way? And I'm going to use first a simple way and then a difficult way. And the difficult way is much more interesting, actually. So what I do is I keep the ordering, and I just have them in sequence, and I add them up, divide by 2, and call that the new threshold. By doing that, I have now conserved W, I mean the energy, for those every second points up there. And what I will then do, and this is just the way the renormalization group is done, I look at my parameters. D is then transformed into D prime, kappa is transformed to kappa prime, and the damage is to damage prime. And what we need to do now is to follow this. This is trivial. This is staying the same. This is just doubled. And this is the interesting one. Now, let's look at uniform distribution on the unit interval, so I have something concrete. Then this energy is then, the integral is then simply d cubed over 3. Okay? And here is the flow diagram in this renormalization group. Here's kappa. And as you iterate, you flow along here. Kappa goes up, 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 up. And you should now imagine a third axis where you have delta. But delta doesn't change, which means that as you go through here, you're always staying at the same delta level, so you can just project it all down here and use colors to look at them. So here's delta equals 0.1, 0.2, to blah, 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 blah. And here one iterates. And this is where there are so few fibers left that you're being pushed around by the system. I mean, you're pushing either this way up or this way down. It really doesn't tell you very much, this one here. But you can have some, but the interesting thing here, and this... Yeah, you have one here, and one here. Yeah, 3. You have one unstable. This is the max point, and then you have stable, no damage, and stable, all damaged, and then you have the critical point right here. But this way of, we call it order space renormalization group, doesn't give much here. I'll give you a little bit more in a second. But the point is that we won't use this one, because how on earth would you generalize this when you have spatial forces in your system? You can't work in order space anymore. So this is just an exercise, this one. But it's nice because you can actually do it. Now here are the threshold distribution. What happens as you iterate and look at the threshold distribution? And you can show, this is a flat distribution between 0 and 1. And we just pull them apart to see them. And all you see is that the fluctuation is going up because there are fewer fibers, but you don't change the threshold distribution. And any threshold distribution will be a fixed point distribution. It just doesn't change in this. Because you're not changing the fiber bundle, you're just coarse graining it. So here is what the force load curve looks like as you iterate. You can see these are finite size effects. And so here, this is when you really are very few fibers left. And you look, for example, at the maximum here. And it goes like this, and then it jumps down. And here are the numerical data on top of the analytical calculation of this. So you can do everything here analytically. All right. Now, and here comes the real thing. And here there are things still, a lot actually, to get from the equal load chain before I think we understand it completely. And once we understand it completely, it's local load sharing time. All right, so we are back to having this transformation of the thresholds. So we transform the thresholds in such a way that the dissipation in the system remains the same under this transformation. That is all what we want. And what I'm saying now is, rather than having the fibers ordered in sequence from small to big, they are sequenced, they sit like this in space. And I'm now simply taking the nearest neighbors in space. So this is a real renormalization group of the standard type. So there it sits. And as I say, this is necessary if local load sharing model is to be studied. The other one will be worthless, I think. Now, what happens? You start with 2 to the 13 fibers, and you start out with a distribution like this, for example, or you start with a flat distribution or whatever. And then you start iterating. And now these threshold distributions are not fixed point distributions, they evolve. And what you can see is that it narrows. For each time, it narrows down. And we can, starting from a flat distribution, it ends up with a Gaussian. Here it is, the Gaussian, 1 over square root of n, and then t minus 1/3. We understand the 1/3, and this is usual fluctuations. And we see this. So you always end up with a Gaussian distribution. I suspect if you use some kind of very, very long distribution with a long tail, you'll end up with Levy distributions here as the static. And I don't know what that tells us yet, but I suspect that this is not the only behavior you'll have. You'll have this for any kind of reasonable distribution, I think. Right, okay. So you get the Gaussian. Here is the flow diagram of the parameters. So here is the elastic constant, kappa. And as we iterate, it flows like this. And here you can see in a completely different way than the boring one. I will show you that there are two stable fixed points here, fully damaged, no damage, and then the critical point. We have not been able to do this analytically. That just simply is too hard. At least, I mean, I've tried all of last month, but you know, just too tough. Here is the force load curve. And it starts out as a beautiful parabola, and then it gets skewed, and ends up being a triangle like this. It goes towards a triangle. And here is the max peak strain and the peak stress. They start out being very different. I mean, this is 1/4, and this is 1/2. You know, I mean, peak strain halfway, the top of the parabola here, and this is at 0.25. And here you can see as we iterate, they approach each other, and then suddenly they do this. And we understand this point here because that point has to be the same point as in the order statistics, I mean order space renormalization group, because there are only one fiber left. So this point we understand, but why it does this in the middle, I don't know. All right, summary. The fiber-bundle model hovers on a border between analytically and numerically tractable, and it is an icing model of fracture. And what I left you with now, and that is supposed to be a very good strategy, is bunches of questions. And some of them probably low-hanging fruit. Okay, so thank you.
Thanks very much for both the lectures on the flow in porous media and this short bit and very interesting bit of dialogue. If there are any questions, yes, we'll give the question.
Is there a way you can get a discontinuity fixed point? A discontinuity fixed point?
I don't know. This is as far as I've gotten.
What will you have to change in a model?
To change the fixed point? I think that, okay, the local load sharing model, no, the global load sharing model is the infinite dimensional version of the local load sharing model. So this is in the mean field limit. What is lacking here are the forces here. The fluctuations are gone. And that's what we have to try to understand. And I think there are two strategies here. Either we just try to do a computational renormalization group and just do that, or we have to do some kind of perturbation type behavior. I'm inclined to do the numerics because I have suspect that the analytical one will be very, very tough.
Don't you suspect that it may be as hard as solving the easing one?
Oh, could be. Yeah, could be. Well, actually, you know, something I would have talked about here if I. Yes, you know, it has to do with percolation. This is actually directed percolation. It's underneath here. I have a postdoc in Trondheim now who's an expert on these things, and he's been able to map. And directed percolation is taking off now. You know, for example, in turbulence now, this is the hot thing. You know, fully developed turbulence.
It's interesting because in imaging of porous media, we are also claiming some directed percolation process.
Yeah. Yeah.
We'll see.
Yeah.
People don't believe in this. Okay, so thanks very much.
Thank you. Yep. All right.